Hello everyone. This week we're going to be talking about mining massive data, and with this we will discuss data that is too big to run your algorithms on in a feasible amount of time, but also data that is too big to store in your local machine, and therefore you need some other methods to still be able to either run anything on this data or process it in some way. So we will be looking at parallelization first, which is basically distributing your processes amongst several cores of your CPU. We'll then be looking at some techniques that make use of parallelization, which are bagging, boosting, and also batching. And these in some part overlap with distributed computing, so we'll also go into that. And during this we'll discuss random forest, AdaBoost, online learning, and then for the distributed part, distributed file systems and MapReduce. So we've been discussing many techniques that either handle data some way, do some pre-processing, run algorithms on your data to do predictions. And up until now, we haven't really dealt with very big data sets or very big models with a lot of parameters, fitted values, these kind of things. Up until now, we've only been focusing on working on one machine. And in reality, when you are working on one machine, you have limited resources. Now, it doesn't really matter if this is your laptop or it's some powerful server you're working on. At some point, you're going to be running out of resources once you reach a certain level of data that needs to be processed. Now, some domains naturally have a lot of data. For example, if you're doing anything with social media or stock market, sort of time analyses, brain data, all these kind of sort of live streams that yield very high frequency data. Those are typically the kind of sources that you will run into these kind of issues. Now, as you know, storing data costs either memory or, in a very simplified way, just costs you hard disk space. So if you don't have a large enough hard disk, you will run out of actual capacity to store your data. But also, when you want to do computations on it, it needs to be loaded into memory. So having your data ready for computation already costs you memory. And then there's also these algorithms that we need to run that cost us CPU power. These calculations need to be done on your processor, and if it's not fast enough, it will just take a very long time to do certain calculations. And with this, especially for the CPU, the most important thing is that we want to run it within the time that we have available, right? So it could vary between like an hour or a week or a month or a year. But at least we want to make sure that it finishes before our human time is up, right? And then on top of this, tuning algorithms might cost a lot more of both. So both more memory, more CPU power, and at some point it's very likely, even with smaller amounts of data that are, still fit on your local machine, in terms of data storage capacity, but just the hardware specs might not allow you to do as much as you want to. So at some point you're going to run out. And what happens if we run out? What can we do? Well, there's 4 sort of options. I mean, these are not exhaustive, but these are the 4 options that we'll be discussing in this lecture. We can run several processes at the same time, so that means we try to have certain workers doing the same work at the same time, which is parallelization, which we'll get into first. Then we can also use less data and then combine multiple models to do our predictions for us, which is bagging. And we can also use algorithms that train incrementally, so they process data in a sort of batch, small batch, or maybe even per instance. And we can also do most of these tasks above on multiple machines. So not only one, but we'll run it in sort of a distributed setup, which might be a cluster, but it could also be just a sort of farm of smaller machines. So let's first get into what we mean with parallelization. Now, while working with scikit-learn, you might have seen this njobs parameter that you can set. And it takes several values. You can set it to either 1, which will use 1 core of your CPU. You can set it to the amount of cores that you want to use, or you can set it to -1, which will just use all of your cores. Now, if up until now this has been a bit esoteric for you, what does this imply? Well, in your CPU, there's multiple cores that can do a single computation task per core. Now, depending on if you have either a Windows machine or a Linux machine or a Mac machine, you might have seen any of these graphs within your task managers that indicate CPU load or memory load. And they basically tell you how many cores are being used for which tasks. Now, in scikit-learn, you can find this njobs parameter to set the amount of cores that you want to use in, for example, grid search, cross-validation. If you have multiple classes, logistic regression can also be fitted over several cores. K-means can do initializations over multiple cores, and these will all make so that there's multiple workers at the same time working on sort of the same problem, and therefore in the end this will speed up the job. So what do we require to have a certain computation task run in parallel? So this sort of depends on the programming language that you're using, also the sort of algorithm that you want to implement, but in general we prefer to have a single data object that we sort of get information from. Now, we might sample from this and just take a bit of it. We might split it per process, but what we generally don't want to do is make alterations to the original object. And why that is, I will illustrate with a small example, but let's first get through the other points. So what we also want is multiple similar tasks so that we have sort of clear structure where we understand that this is almost the same job as we try to do on one core, but we just want to do this single task twice, but then with a slight change, we might want to therefore push it to another core so they can run in parallel. So imagine that we have this matrix of numbers right here. For a computer, this could be very easy to sort of give us a list with frequencies for each of these numbers. So I want to know how many times does 10 occur in this matrix, or how many times does 1 occur, and so on. And in the end, I want a list with the frequency of every number. As humans, we might just look at this and say, okay, well, if I can just focus on one of the numbers, it's kind of visually easy to deduce that there's a particular amount of numbers. We can cheat with our visual system and just sort of diagonally scan this matrix, and we don't have to really look at each number one by one. But imagine that we do, because this is when you run a certain computation process, this is how it works. It iterates through this matrix cell by cell. And if you don't have any fancy ways of speeding up this computation with some linear algebra sort of matrix magic, you'll have to go cell by cell, which is a pretty computationally intensive process. So imagine that as a human, you are just provided these numbers one by one, and you have to remember how many numbers there are for each of the numbers, right? So we want this frequency per number. Now, a computer has a very nice trait that it has a very permanent memory. We can just count these numbers and then store their frequencies into memory, and it will just keep a list, basically. So it's as we would have to do it, and then we can also cheat by having a piece of paper that we just write the counts on, right? But assume that this paper is also limited, so we can only look at one number at a time, and we can only write down one number, so the frequency of one number. Now, this is where your memory capacity is definitely not enough, or at least your active memory capacity to remember more than some amount of numbers and their counts, definitely not 10. And similarly for a computer, if it can only store this many numbers, it will have to go over the matrix several times, right? Now, the easiest thing for us would be to just get another person to also look at this simultaneously as you are doing. This person can look at other numbers, and you get another one who looks at another pair of numbers. And once you reach 10 people who all count just one number while the numbers are appearing on the screen one by one, then you wouldn't have to repeat it 10 times, right? So that's a distributed work over the same object, and is therefore basically parallelization. Now, this not altering the object itself while doing computations is important, because if, say, one of the tasks of a person was to subtract or sort of change a number on this data object that we have, so by the time that all the 10 persons have reached the end of the matrix and one of the numbers has changed, it could be that this number has changed after a person has counted the frequency of the old version of this number, and therefore the frequencies won't be correct in the end, right? So hopefully this sort of illustrates why we don't want to make any alterations to the original object. Now, we can obviously, in some cases where it's not really important what the previous state of the object was, so if we only have to go over this once and then we only want to have the counts for the original matrix and it doesn't really matter how the new state is, then obviously it doesn't matter, right? We can make alterations however we like. But if we want our counts to be true in the future as well, then we can't make any alterations. Okay, so now for an actual applied example, we'll look at how this parallelization works for cross-validation and grid search. For cross-validation, we can, for example, assume that we have 3 divisions of our data, so basically 3 splits or 3 folds. Where this is val, this is val, and this is val. So we have the original data object that doesn't change while we're doing operations. The only thing that we want to do for the other processes is give the sort of index of the splits to a certain process. So let's assume we have a quad-core CPU, so it has 4 cores. We would want to have this job of training on this part and then testing on this part distributed to the first one. This one goes to the second one, and this one goes to the third one. So these cores will now start running a classifier simultaneously. So this would be, say that we're running KNN, then there's a KNN running on this one, there's a KNN running on this one, and there's a KNN running on this one. So this will yield one score, this will yield a score, and this will yield a score. And then in the end, we just collect amongst, once everything is done. So there's no guarantee that these 3 will sort of finish simultaneously, but we'll just wait for the last one to finish, and then after all are finished, we just aggregate the scores. We can just fetch them from the different processes, and we get a list with the 3 scores. So this is how it works for cross-validation. And for grid search, you can imagine it works the same. We have this sort of grid parameters that we came up with. So let's say we're tuning C for SVMs, and we have these 3, or let's say 4 values of C. Then equally we distribute 1 to core 1, core 10, core 2, core 3, and core 4. And these will also run SVMs in this case, so not KNNs. Let's just change this into SVM. But then with a different parameter setting, right? So this one will run 1, this one will run C is 10, this will run C is 100, and this will run C is 1000. Again, we get these 4 scores, we aggregate them, and then in the end we can collect them. So if you're working in a programming language where you can just pass the indices that we need to fetch to collect this to the process, then this won't cost us much additional memory. We just incrementally send those to this core that we have here, and then finally train. And there's different optimizations that you can make to not make KNN use a lot of memory for this particular parallelized implementation. And because we're doing this simultaneously, it will only take us as long as doing one operation, right? So if we would do it sequentially, this would take us for almost 4 times as long. But now that we're doing it in parallel, it would just take us 1 time as long, approximately, right? There's a bit of overhead, but we can assume that it's somewhat close to just running one process. Now the question that I have is, can we run both in parallel simultaneously? And the answer is no, we can't. At least not when we're doing both grid search and cross-validation. But this is only assuming that we're maxing out our CPUs doing grid search or cross-validation. So say we have 20 cores and we're just doing cross-validation for 10 folds, then obviously we have some CPUs left to do another grid search simultaneously. But do note that for doing cross-validation with 10 folds here, and we're doing grid search of 2 parameters here, then we would need 20 cores to actually run this simultaneously, right? So this multiplies. Now, if you're already maxing out your CPUs, there's no way that you're going to stack another of this process, right? So again, also 20 cores is very rare. Those are like very high-end current CPUs. Or any cluster machine might have this available, but in general, you're stuck with either 4, 8, maybe 16. Okay, so hopefully you now see how parallelization sort of runs almost the same jobs amongst different cores, and this yields some speed up. Now, grid search and cross-validation sort of focus on a different level than the model itself, right? We just run several instantiations of data splits or of the model with different parameters, but this is not necessarily making our algorithms parallel, right? The processes within this algorithm and how it works isn't parallel. And what you will see is that the majority of classifiers actually doesn't run in parallel because you require all information, especially when you're working in a vector space, to be available at every time step. So we can't just split up the vector space because we need access to all of the instances at once, and doing this split will be either very computationally inefficient, where we might as well just do it in one go, or it will just literally not be possible due to the implementation of the algorithm. However, there's a special class of algorithms that does allow, or at least partly allows, parallelization, and these are ensemble methods. And specifically within ensemble methods, bagging is a very good example, something that runs in parallel, and batching might also be one. However, given that we're now talking about ensemble methods, I also want to tell something about boosting. Boosting isn't necessarily something that can be run in parallel, but I think it's a nice sort of example to get started with. So within ensemble methods, we distinguish boosting methods and averaging methods. And these sort of differ in how they treat the ensemble of classifiers or regressors, so predictive models in general, within their implementation. So boosting iteratively stacks models to reduce the bias of its combination, which means we train multiple models. We start with, usually we start with a very weak model, and we try to incrementally make it notice or sort of fix this bias that we notice in our initial weak model. So we sort of know which are sort of the instances that are, for example, easy to classify. We know which ones are harder, and by incrementally paying more attention to difficult ones, we might improve the model, which is an implementation of AdaBoost, which we'll talk about a bit more on the next slide. But we try to sort of incrementally make our models more complex, cover more edge cases, and in the end we sort of ensemble all of these different versions of our model together to make one prediction. And this is exactly the same with averaging. However, we don't necessarily want to fix the bias, we just want to train more algorithms. So we could, for example, take smaller samples, divide our data set into splits, train, for example, k and n 10 times on 10 splits, and then use these to all make a prediction regarding one single instance. So we might get 10 predictions. And then in the end, we can, for example, do a majority vote or look at the outputted probabilities if it's a model that takes into account probabilities. And we might do some extra fancy tricks. And this will be an implementation of, for example, random forests. And then the first thing was bagging. And we'll also talk a bit more in detail about that. Now, ensemble methods, if you have the resources available, they can cause a bit of speed up in the fitting of your models, because due to the fact that you're doing the splitting of data, you can do parallelization. And because you're training these models on smaller amounts of data, you might decrease your memory load. So you can sort of trade off the sizes of data and the amount of classifiers that you're training at the same time to still run in the same time that you would be running one model, or even faster. And then as a sort of bonus, it also makes your classifiers more robust in general. So they will have a lower prediction bias in the end. Okay, so let's first take a look at the implementation of AdaBoost. The process is generally somewhat described like this. So we have our data. This will be our train, and this will be our test. And what AdaBoost does is that it samples from our training data instances into a bag. This is our bag. And what we do is we throw a bunch of instances in here. And we train, for example, let's say a very simple decision tree, which is also an important realization. So this ensemble method of AdaBoost can take whatever estimator or algorithm, or however you would like to call it. You can throw it in here and see if it's improving. So this AdaBoost is a way of handling multiple implementations of either classifiers or regressors. Anyway, so we trained our decision tree. Usually we start off with a very simple model with a lot of error, because this will allow us to look at the problematic instances, which I will indicate here by crosses. So let's say we did very poorly on these. So for example, we had very high confidence that these were actually in the other class. What does AdaBoost do? It creates a new bag. Also important to realize, which I forgot to mention, is that this decision tree is actually tested on the training set. So we use the training set to test this model right here, and then we can sort of identify what the problematic instances are. Anyway, so once we've done that, we want to give a bit more weight to these problematic instances. So we might, for example, throw in more of the problematic instances, so sort of oversample them. If there's a classifier that, for example, can just allocate more impact on these particular instances, we could also use that. However, it's a bit more complex to explain, so let's just assume we just oversample our problematic instances, and then the ones that we did very well on, we might not want to sample into this new bag that we have. So we might double throw some of them. Some of the problematic ones we might have in there multiple times. And then the easy ones, either not or not so many. Let me train another model on this. Test it again. Just repeat this process over and over until we also classify the problematic instances correctly and therefore reduce our bias. Now in the end we sort of wind up with multiple versions of our decision tree, and we use these all at the same time. So we aggregate all the predictions of all these models that we have here to come up with multiple labels for only one instance. So this is also important to realize. So it's just a single instance that we have here will have multiple predictions, and we can choose how we would want to go about weighting the predictions of any of these classifiers. We can, for example, look at weighting them according to their performance. We might just do a vote where we say majority counts, or we might fit another classifier to sort of determine which of these bags are actually correct. Any of these would do. And if we have a probabilistic classifier, we might also just average the predictions. So we average the probabilities in the end. As I illustrated here, this is just using a single model. So the question is this algorithm, do you think it can be run in parallel? And the answer to this question is no. At least AdaBoost in its original form is not implemented in parallel, because we need the classification error of this first model to continue training our next model. So at least with most of the sort of estimators or models or algorithms that don't have a parallel implementation, we can't make AdaBoost parallel because we need this previous state in order to continue. However, this is a very, very good method of reducing bias and having stronger final models. So this is why I thought it would be worth mentioning. Also because it somewhat overlaps this sort of intuition that we're sampling into multiple bags with the next thing that we're going to talk about, which is bagging. Now, compared to AdaBoost, bagging is actually very straightforward. We again have this data of ours. So we have a train and a test. Oh, this is a bit big of a test set. Let's make it a bit smaller. Okay. Now for bagging, the thing that we're doing is also making these bags of instances, but rather than determining their contents based on some performance of the previous classifier, we're just going to toss in some percentage of our data. So we're going to randomly sample these in. So let's say we pick a sample rate of 10%. 10% is going in this bag. 10% is going in another bag. Or at least, I mean, these don't have to be necessarily divided over the bags. We can say we want to sample 10% but only have 3 bags. But at least these bags individually will have 10% of the data, but they might not. They might have some overlapping instances here. Now that we have these bags, we can choose what to do. So we can either take the same model over all the bags. So we might use KNN for all of them. Or we might decide that, okay, I want to fit an SVM on this one or a decision tree on this one. And in fact, we can do the same with just having 100% of our data just training multiple models. But the idea is that when we train a single classifier on smaller amounts of data, then the samples that are very biased or yield a biased classifier won't weight that much. So typically what we do is that we fit, at least when we're using a sort of proportion of our data, we fit only one classifier. And you might want to repeat this after with more different classifiers trained on smaller data, and so you can sort of stack ensembles together if you have enough time to train all of this. And it sort of works the same in the end, so we just aggregate the predictions for a single instance. And we can use sort of the same method, so either averaging or voting or whatever you prefer. And then the sort of good thing about bagging is that because we sort of run the same kind of processes and there's no interdependency between these in terms of results, we can actually do this in parallel. So we can have one thread per bag or per classifier that we train on these bags, which is good. So this makes it very fast, in a very fast way to either train on smaller amounts of data or train and aggregate the predictions of multiple classifiers. Now, random forests use this kind of bagging method, but they have a special tree implementation where on top of doing this sampling of data, they also choose random features for each node. So remember that with decision trees, we want to choose to split on a certain feature. Now, for each of this node, so for each of decision that we want to make, we just sample the amount of features that we might consider to split on given our information gain or any other metric that we're using. So we just remove some, and this results in also in a very robust classifier because it can't use all of the features at the same time. So there will be some error and some weird branches in this tree, or at least a set of randomly split trees. So this is why it's a forest, so we fit multiple of these trees, and then in the end we aggregate their predictions. But due to the fact that we're using bagging and we're trying to fit multiple trees, we can run it in parallel, which makes it a very fast and also very good implementation. So for most classification problems, random forests or boosting methods are actually very state-of-the-art performance-wise. And this is due to the fact that they run so fast, they might use less memory, but they also generate multiple sort of noisy classifiers, which when aggregated actually have pretty robust predictions. So just to recap, fitting single models is very costly. We can train many smaller models using, for example, bagging. And the way that this works so well is that after we fitted our classifiers, we don't need access to our data anymore. We can just look at the fit of the model to do the predictions. The fit isn't related to the data in a very strict sense. So for example, if we're fitting logistic regression on this cloud of data right here, and once we have our line, let's make these sort of thicker so it's clear that these are different classes. So once we've fitted this line of us, we can just take the coefficients for this line, and we don't need the data anymore. We just have this model, so this function that is just a value for the intercept, and then for, let's say, coefficient that we fitted, and we can just take these, and that will be our model. So even though we have a lot of data, the final model, or sort of the values that we're using here to make predictions, is actually very small in terms of data. It's just this one formula, or multiple, if we're doing multiple logistic regression, we will have a line per class, right? But compared to our data set, this is probably very small. So this is why fitting multiple models on a lot of data is sort of a smaller approach in terms of memory use than doing one large one. And this is why fitting multiple classifiers on small amounts of data won't result in a very big set of data after we aggregated them all, because these are the values that we're fitting, right? If we put these together for multiple small ones, it's not going to blow up as much. All right. So another special way of handling large amounts of data is through streaming our data to our model, or just feeding them per instance or per batch. So say, for example, we're doing a spam classification task and we're fitting naive Bayes for this. We can actually feed the data that we have per instance to naive Bayes, because it just has to update the probabilities for each of the instances that we have, and it can just increment the probabilities. So say that we're starting off with just 2 features and a label. So we have free and lunch, and a label. Let's say we have S for spam and H for ham, so no spam. So this is S, H, H. But imagine that we're just feeding this one by one. So we start with spam 1, which has free and doesn't have lunch. So we can already update our probabilities that free occurs 1 out of 1 times given spam, and spam occurs 1 out of 1 times. Right? Now we go to the next one and we see 0, 1. So now we have to update our probabilities. So this becomes 2 out of 1, and 1 out of 2 will be, so this was free, and this is lunch, and then spam occurs 2 out of 2 times. Let's just put this here. Then we go to the next one, which is lunch, and it's not, so we have to make a lunch one for ham. So we need to update this one to 3. We have 1 out of 3 ham, and lunch is now 1 out of 1 times under ham. Then we get free under ham. So now we also need free here. It occurs 1 out of 2 times. We update lunch to 2. We update ham to 2 over 4. And spam also 2 over 4. So this is exactly how online learning works. We can also do it in batches of multiple instances, so we might do it a bit faster. This is also implemented in neural networks, which we will discuss in another lecture. However, do note that we need algorithms that support this, so that have this sort of incremental way of accepting data and not needing this vector space for calculation. So if you would imagine KNN, we need all the instances in memory to do this distance calculations, right? So we can't have them just iteratively inserted. We can have them iteratively inserted, but we need them all at the end to do the distance calculations. So in the end, we'll end up with a very large vector space anyway. So this also brings us to the drawbacks of doing ensemble methods or online learning methods. Now, while bagging reduces CPU time, it might increase memory. The other way around, when we sample too little data, we don't use a lot of memory, but it might take longer than actually running the model once. And with online learning, we require specific algorithms. So if we need something in particular, so for example, you really need this tree that is fitted by decision trees, you can't do that. So you need to take another approach. And actually, online learning might also take longer. If you have a lot of data and need to pre-process it, and you all need to do this while streaming your data. So say, for example, you're just plugging into a feed of emails and updating your spam filter while the emails come in. This could actually take longer than doing it all offline, where you just store the emails and process them in one go. And obviously, because you're keeping all these probabilities around from naive Bayes, for example, it might still be that you run out of memory. You might have way too many probabilities for features that don't occur a lot, so you might want to kill them at some point, but given some very huge vocabulary, you will have a lot of words hanging around anyway. So your system does need to support the vocabulary if you're working with text data to not run out of memory. However, given the fact that we can split up our computations, we could potentially move away from a single machine. And this is exactly what distributed computing does. Now we can sort of split up distributed computing in two different approaches that can be handy for us. So we can either distribute our models amongst different systems, but we could also distribute the data that we're handling amongst many different systems. And this will most likely solve some of the issues that we're going to run into. Now, one of the drawbacks is that I can't show you very practical examples, because companies that need distributed computing are very, very large. And the landscape of these tools is so huge that you need a very complex setup with a lot of different components to make this run very quickly. So some of the things that we're going to talk about are just not feasible for me to show. There's some video tutorials and some demos that you might be able to find on the internet that will exactly show you how this is done. I just can't show it here. Anyway, so let's go into the first part, which is distributing our machine learning models. And I think this is, at least if you have multiple servers available, this is something that is still feasible within a sort of smaller scale setup, either for research or for a smaller company that is not Google, Amazon, or LinkedIn. And this is using the techniques that we've already discussed. So, for example, bagging, we can actually distribute the samples of our data amongst many different machines, which would also allow us to use very sort of low power machines. So you don't need fancy servers, you just need a bunch of cheap computers, and you can sort of distribute your data over these different machines, so they also don't need a lot of storage space. You can fit your models there and then in the end sort of ensemble them together on one machine that you will deploy them on. And similarly to, for example, doing online learning where we're using naive Bayes, we can actually have a version of naive Bayes per machine and send our stream of data between these PCs. So just send one packet to one, another packet to the other, and in the end we can sort of aggregate these probabilities once we're done, because they're just counts, right? They're counts for vocabulary, so as long as our final machine can fit the entire vocabulary, we can use these smaller systems to do this aggregation for us. Now we could also, because you might say that, okay, if we have this final machine available, why are we even distributing this? You could also bag naive Bayes, right? So you can actually make it online and also bagged. Then finally, we just aggregate or sort of distribute the predictions. So we might send a single instance to multiple machines and then have these machines do the predictions for us. So this might look something like this. Just to very quickly draw it out for you. So we have a bunch of machines, let's say. And we have this big chunk of data coming in a sort of stream way. So per sort of 5 seconds, let's say. That's very optimistic. We get one instance. So per instance, we just, at least in an online setting, we just send it off to one machine. We send the next one off to this guy, next one off to this, and the next one off to this. And this machine will do some probabilities, this machine will do some probabilities, this one as well. So they all have their own sort of naive Bayes instantiation. And then in the end, once we're done with streaming all our data, or we could even do it while streaming all of our data, we have another machine that has this thing we want to predict available. So our single instance. And we just send it off to all of them, etc. And then after we sort of aggregate the predictions of all these machines, so they just send the prediction back, we get 4 predictions here, and we can just aggregate over them, maybe average the predictions or the probabilities, or do majority vote amongst them, whatever we prefer. This sort of solves our machine learning part, because we can use a lot of systems to just do sort of simple local computations. But if we actually need to do things with our data that require us to have a very big overview of our data, or we need all data available, or all the counts, for example, available of our words, we can't just simply distribute that, because we need, at some point we're going to need the entire batch of data available to us. So we need sort of a smart way to chop these blocks up, then same as we're doing here with just distributing it over multiple systems. We want to sort of do very small local computations and then in the end aggregate them, so that the bulk of the work is already done. We don't need these big documents, for example, in memory to do any final sort of computations. And this way we could do feature extraction for our words, as in building a vocabulary and then having counts per document. Now this is exactly the sort of thing that Google was working on in the 2003, 2004, probably way earlier, but they released 2 white papers around this time that described both the fast system they were using for doing this sort of distribution of gigantic collections of data, and then a technique of aggregating any sort of counts or small operations on this huge batch of data, which was then called MapReduce. Now these spawned a lot of different things that you might have heard of, for example, Hadoop, Spark, Hive, Pig, HBase, HDFS, all of these ecosystems for dealing with large volumes of data. And it has been just increasing every year. There's some new thing coming out that is supposed to even better handle all this data and do computations very fast. Now, as I said before, there's only very little companies that actually deal with such big volumes of data that they can't be stored on single machines. Just to think, you can buy like 6 terabyte hard disks and you can chuck a bunch of those in one system up to, let's say, 10. So if your data is not bigger than 60 terabytes, which is already a lot of data, you don't need all of this architecture, right? If you don't run a very big data-oriented company, it's usually a lot of overhead to invest into this gigantic landscape, as we would want to call it, that surrounds these large volumes of data. Because all of these sort of interact, and generally you need a lot of knowledge to operate all of these independently, or sort of know what the advantages of one system is over the others, and it can become quite the mess. However, it is very interesting to talk about, I think, so I just want to give you intuitions regarding how distributed file systems work, and then how to run sort of MapReduce tasks over these distributed files, and then do very quick aggregation of data. So let's get into it. So the first thing that we will talk about is how to do distributed file storage. So here you'll have to imagine that we have a bunch of servers that host a lot of different pieces of data or collections, and we'll just assume that we're talking about documents here. Now, documents can obviously run into many large volumes. Let's say we have a collection of books. It might be very likely that some of them are quite expensive to go through to count all the words, and even though it's just text, it might still become troublesome to just go through the entire thing. And here we're talking about milliseconds, right? We don't want to spend too much time counting all of these different items if we have some customer on the other end that needs a response from the server very quickly, right? If, for example, you ask for a recommendation on Spotify, for example, you want this response to be very fast. This calculation needs to be done very quickly. Okay, so the idea here is that files can be chunked. So we have this document of ours. So this is this one document. And we want to sort of get this counted. So we want to count the words that are in here. Now the way distributed file storage works is that it just chunks up this document into splits. So we have split 1, we have split 2, we have split 3. And you can sort of figure out that if we have the word counts for split 1, if we have the word counts for split 2, and we have the word counts for split 3 individually, then we have the word counts for the entire document, right? So if we can sort of distribute this to different processes, then we might run them simultaneously or in parallel, and that's pretty quick. So one of the things that companies are also concerned with is data retention or protection, or however you want to call it. They want to have some redundancy in terms of having copies of some particular split, so that if one of these things dies, we don't lose data. That is pretty important. So the way that most distributed file storages work is that this document split, so let's say we have split 1 here, we also have split 1 here, we also have split 1 here. So let's say we just copy it 3 times, then split 2 goes here, 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 and 3 goes there, there, and here. Now, obviously, these servers will have way more than just this single document, but this is just to illustrate how this works. So now we have some sort of redundancy. So if this server here fails, we have access to document 1 here, or at least split 1 here, and split 1 here. So we didn't lose this data, which is good. Now, another important thing to realize is that if we have a system that wants to do computations on this split, we would want to access it as soon as possible. So for looking for these splits, one server needs to sort of descend down the file list, let's assume. There's way faster ways to do this, but let's say that the server does this incrementally. It just has to scan along all of these to finally reach split 1 right here and say, okay, I have document 1, I can start computations now. Now, logically, the server that we would prefer for doing computations on document 1 is this one, right? Because it has 1 as one of the first elements in its file stack. So we need some node or a computer here that has knowledge of where documents are indexed in these different servers. So this doesn't need to store the data, it only needs to know which batch is on which node, and how far up in the index is this, because then it can distribute the computations efficiently. So it can say, okay, you say that we want to calculate the frequencies for document 2. Let's call it for this example. I want the frequencies of document 2. I know that split 1 is on this server, so I'm going to make it do the counts of batch 1 first, and then this guy over here has to do 2. So 1, 2, and this one has 3 first, so we want this one to do 3. Now, if we assume that this server failed, we can just off-ship this calculation to some other machine. Usually, we have them distributed over many more machines, so we have 3 copies, but we make sure that this document 2 is actually spread over multiple servers and not just on 3 only. So 1 might be here rather than there, for example. So we have it scattered a bit more, so that if we determine that this one has 1 first, this one has 3 first, we can also off-ship our computation to here, to another server. Anyway, so this is distributed file storage in a nutshell. There's a lot of programming going on between sort of this distributing, sort of allocating the jobs to different servers, how to handle these fails, for example. There's also work in distributing and chunking the files correctly, and also making sure that if a job is issued to these servers already, so these servers are already busy, that this is sort of optimized, so you want to have servers that have a unique combination of documents. You want it to be available for those, and sort of optimizing this allocation of different jobs. Anyway, that's way out of scope here. I just wanted to show you how this works in theory. Now, once we've distributed all of our documents and we can actually submit jobs to different servers, we need a way of correctly handling the counts and aggregating them, right? We have these chunks, and then finally we want to aggregate them to one list of word counts. And this is exactly what MapReduce does. So MapReduce, you can sort of imagine as several mappers counting a batch from a document that they obtained. So let's say document 1 or document 2 has these batches or splits, and here we have the ball, and here we have the cat, ball, and here we have cat, jump. Now in the mapping phase, different mappers are allocated these different splits. And what we do is we turn all of these into key values, where the key is the word and the value is the count of that word. So mapper 1 will come up with the ball and which all have a count of 1. And the second mapper will have the 1 cat, 1 and ball, 1. So these are different systems, right? That they have this sort of separated from each other. And this one has cat 1 and jump 1. Now that we have these counts, we sort of need to aggregate them. So one of the things that is done is the shuffle phase, and in the shuffle phase, these are sorted by this could be alphabetically, and then distributed to different reducers. And the reducers have the task of just aggregating the counts. So we send them by key to different reducers, so all the thus are going to our first reducer. So it will have the 1 and the 1. Then we have 1, for example, for a cat. So we have cat 1 and cat 1. We have 1 for ball, for example. We can just continue this, so I'll just stop here. There we go. We can also split this up, so we can give one reducer all the words that start with A, the other one all the words that start with B, etc. As long as it's sort of distributed over all the reducers that we have available. And then in the end, you are left with the count, so just summing these up, cat 2 and ball 2. So there we go. This is literally the most naive implementation of MapReduce, but this is how it works in theory. Now there's many algorithms that you could think of having this property of not being able to fit all the data that we have, and us having to sort of off-ship it to different workers, different systems that actually can handle smaller volumes of data, or to some extent approximating this, so maybe we don't care about having full precision over the entire vector space, and we can implement, for example, naive Bayes or support vector machines in this sort of MapReduce job kind of style. These are, for example, implemented in Apache Mahout, in Storm, and Spark, all these sort of frameworks that have machine learning libraries in them. These are therefore sort of commonly used in industry for doing fast computation, and specifically distributing jobs amongst different workers and having this data retention, because that's also an important part of it. Alright, so that's the end of this video lecture. Hopefully you're now sort of aware of how to distribute not only your tasks amongst different workers in terms of different cores on your machine, how to avoid large memory load on your single machine, but also how to sort of distribute data and computations amongst different systems. Now, as always, if you have any questions, I gladly refer you to the forum.